Hello all. Even though we are in the middle of the summer, and actually the Cypriot summer, which is really brutal, I'm not a summer guy. I don't like summers. I only like winters. Okay, it's too hot for me. I hate it every time. Yeah. So I had to say that. I have this. Let's call it leftover paper, which means that I went through solving this paper actually, I think maybe more than a month ago, few weeks back, I don't remember. But every time I tried to record it, something came up, someone interrupted me, or I had something else to do, so I stopped. So, anyway, I hope this time I will record it. It would have been way more useful if I had recorded this a month ago so that people would use it for their exams, but better late than never, right? So, this is a mathematics paper, mechanics, okay? I haven't delved into other mathematics papers yet, and I don't know if I'm gonna do that. We will see. I'm still thinking about new content ideas and so on. So this is the most recent international A level from January 2026, as you can see in your screens, okay? And it's mechanics M2, okay? So I assume this is a level down from the mechanics M3 papers that I uploaded in the past. And let me know in the comments, is this considered advanced subsidiary like AS level, or is this A level? And also there is a mechanics M1 paper that I haven't worked on yet, but maybe I will do in the future. So the general things I always say, the test lasts 90 minutes, 1 hour and 30 minutes, like a soccer game, by the way. And it awards 75 marks. So my general recommendation is that you guys spend about a minute per mark, meaning that if a question awards 10 marks, you should spend about 10 minutes on that problem. So you stay on time, and you score maximum points. And the other general thing is that, of course, go through the problems that you are comfortable with in the beginning. So solve everything that you know how to solve immediately. Okay, don't waste time on things that you don't know how to deal with. So solve everything that you know how to solve so that you build momentum, and then come back for problems that you didn't know how to solve uh, in the beginning after you have solved other problems, so you have momentum. Okay, another problem with this paper is that I don't know how many formulas they give you, so I'm gonna solve the paper assuming that some of the things that I will talk about are actually in the formula sheet that you can carry with you. Okay, so let's dive in and start with question one. So a van of mass 1200 kilograms is moving up a straight road that is inclined at an angle theta to the horizontal, where sine theta is 1 over 14. Whenever they give you the sign of an angle, it means that it appears in the solution, probably, okay? So this is related to a component of a force, as we will see, okay? The engine of the van is working at a constant rate of 20,000 watts, okay? The resistance to motion of the van from non-gravitational forces is modeled as a constant force of magnitude r newtons, okay? At the instant when the acceleration of the van is 0.75 meters per second squared, the speed of the van is lambda meters per second, and r is 26 lambda, where lambda is a non-zero constant. And they ask us to show that r is 260, I assume newtons. I don't know why they don't have the units, but anyway, the first step in these types of problems is to actually draw the scheme of the situation. So we're gonna have an incline, okay, which models the road. Okay, so this is the incline, this is the angle theta. I'm gonna try to make better letters, okay? So sine of theta is 1 over 14. I'm laughing because it's one of the complaints I get in my videos that my handwriting is horrible, which I'm aware of, okay? So I'm trying to do my best. So we're gonna model the van as a box, okay? So this is the van. So that's the center of mass of the van. It moves up and it accelerates upwards, okay? So we are going to analyze forces in the x-axis, and the x-axis is going to be the direction of it's going to be parallel to the incline, I'm trying to say, okay? So first of all, let's do the free body diagram and draw all the forces. So we have the weight of the van that points down, okay? The reaction from the floor, which is there, right? So let's call it N. And then we have the resistive forces that point in the opposite direction than the motion, okay? This is standard. I don't know if I have to say more about this, but resistive forces are usually due to either the wind or the friction, okay? And both of those forces oppose the motion of an object. So if the object is moving forward, the reaction force from resistive forces is always backwards. Okay, so that's the idea. And then we have one more force. Don't forget that they tell us that the engine is working at a constant rate of 20,000 watts. Okay, so we have a force that we will call F engine, and we will deal with in a moment. Before we do that, we need to analyze the weight into a component that is parallel to the ramp and a component that is perpendicular to the ramp. So I'm going to draw this axis, okay? So this is sort of our y-axis, but it's tilted, rotated, if you will. So we need to find this angle, okay? So that angle, I claim that it's gonna be theta, okay? The reason for that is that this side is perpendicular to this side, okay? And then this side of the angle is perpendicular to this side of the incline, and therefore the inscribed angle, which is the angle theta, okay, for on the incline, is going to be theta, okay? So I hope this makes sense. If it doesn't, ask me to explain again. I'm gonna remove all those lines the extension lines that we don't need, okay? So with that angle being theta, let me erase that, the weight, and let's move the letter here so we have space. Okay, and now let's analyze the weight actually. Okay, so the weight is going to be analyzed into a component that is perpendicular. Oops. We're going to analyze it into a component that is perpendicular to the ramp. Okay, and that's our mg, because weight is mg, right? Weight is mg. So that component is mg cosine theta, and therefore the x component, and again, the x-axis in this situation is parallel to the ramp, okay? So the x component, I'm going to draw it there, is going to be mg sine of theta, okay? And you see how sine of theta appears in the equation that we need to set up, okay? Because they gave us sine theta in the beginning, if you recall. Okay, how do I know that that's the cosine theta component? The component that touches the angle physically. So this component, right, that I'm trying to draw now with my pencil, touches the angle theta. So that's the cosine theta. And the other component doesn't touch it. So that's the sine theta. That's how I remember things. Now, let me address what the force from the engine is. So the power from the engine is equal to the force of the engine times the velocity. Okay, this is kind of standard. In case you are not familiar with it, let me convince you with units. The units for force is newtons, the units for velocity is meters per second, and then if we multiply newtons by meters, we get, actually, I need that, okay. So if we multiply newtons by meters, we get joules, and then over seconds, which gives us watts, okay. So F engine is simply P over V, where P is 20,000 watts, okay. And now we have to set up an equation. Let me set it up down here, and then we will turn the page. So with the acceleration and the velocity being upwards to the right, okay, we're going to take the force from the engine as positive, and then we will subtract the other forces. So we need to use Newton's second law, in other words, as follows. So we have P over V, right, minus the resistive force, minus mg sine theta. This whole expression is, so this is the sum of all forces in the tilted x direction, as I called it in the beginning. So the sum of all forces is going to be equal to mass times the acceleration in this direction, okay? And then we also have the equation that the reaction force, I'm going to put it in a box over here. The reaction force N from the floor is equal to mg cosine theta. Okay, we don't need that one. Okay, I mean, it's it's a valid equation, but it's not useful for us because the van is not making any motion in the tilted y direction. Okay, so let's analyze this equation that we wrote down. Okay, now P is equal to 20,000 watts, so I'm going to write 20,000 over the velocity. The velocity is given as lambda, right, at the instant that we are interested in. And then R is given as 26 lambda, right? I mean, they give us all this information there. So R is 26 lambda. Lambda is the velocity. And we're given the power as well. Okay. So minus 26 lambda, and then minus mg, which is 1200 kilograms times 9.81 times 1 over 14, which is mg sine theta. This whole thing is equal to 1200 kilograms times 0.75 meters per second squared, which is the acceleration. Okay, so let's keep working on this. 20,000 over lambda, and then I'm gonna make lambda in the denominator as the common denominator of all factors. So we have 26 lambda squared over lambda, right? Because we need lambda in the denominator, minus 1200 lambda over lambda, okay? And then I'm gonna put in parentheses 9.81 times 1 over 14 plus 0.75, okay? I hope I didn't confuse you. And this whole thing is equal to 0. So what I did here is that I brought this factor to the left-hand side, okay? And then because it becomes a minus, in the parentheses it becomes a plus, and 1200 is a common factor. And then I multiply and divide by lambda. So I'm not doing anything crazy, I hope. Okay, so let's continue. Let's switch back to black. So we can get rid of the lambda in the denominator now, right? So 20,000 minus 26 lambda squared minus 1,740.86 lambda, which is this factor over here, okay? And this thing is equal to 0, okay? So 26 lambda squared, I am switching this, flipping the sign now, okay? Plus 1,740.86 lambda minus 20,000 is equal to 0. And now we will divide by 26 to get rid of that 26 in front of 26 lambda squared. So lambda squared plus 66.96 lambda minus 769.23 is equal to 0. And this is a quadratic equation for lambda. So lambda 1, 2 is going to be minus 66.96 plus or minus, okay, I have my square root, plus or minus, I will do this a little bit fast, 7,560.56, which is of course this factor squared minus 4 times this factor, okay? So it's the discriminant, okay? I just gave you the discriminant directly, sorry, okay? Over 2. And I'm gonna skip a step and give you, no, actually I'm not gonna skip a step. Let's let's write it down. Lambda 1, 2 is minus 66.96 plus or minus 86.95 over 2, okay? And we know that this needs to be positive, okay? So we discard the negative solution simply because the velocity needs to be positive because we are moving upwards, okay? So I'm gonna turn another page. So lambda is simply 9.99, which is 10. Okay, so we take 10 as our solution. And then R is 26 lambda, therefore 260. I assume newtons, but I don't know, they don't ask for that. So part A is done. Okay, now we have to go back now. I will turn the pages and go back and proceed with part B. Okay, part B starts here. Okay, so later on, excuse me, the van is moving down the same straight road. Okay, the model for the resistance to motion of the van still has magnitude 260 newtons. See, so this was a typo. Okay, the engine of the van is now working at a constant rate of p watts. Okay, at the instant when the speed of the van is 12 meters per second, the acceleration of the van is 1.8 meters per second squared. Find the value of P. Okay, this is a different problem, so you have to set up the problem again from scratch. Okay, don't try to reuse this scheme that we made for part A because it's going to confuse you. So let's go set up the problem again. So let me see, do I have enough space? Okay, I do. Okay, part B, we have the following. So this is our incline again. Okay, maybe it doesn't look identical to the previous one, but okay, it should be identical. Okay, so this is our van again modeled as a box. And we have the center of mass as before. So the weight points down like before, and the reaction from the floor is perpendicular to the incline right before. Now, a few things change. The velocity and the acceleration point down, okay? Okay, the weight can still be analyzed in the same fashion as before. So that's the mg cosine theta component. And we have the mg sine theta component. But now the component p over the velocity points, oops. So the component related to the force from the engine points down in this case. By the way, okay, let me try to draw a straight line. Okay, there. Okay, now F engine is again P over V, but it points to the left. And the resistive force is to the right. Okay, and now we have to, let's call this P prime, okay, the new power that we are looking to find. Okay, actually, let me enlarge this a little bit. So let's move this a little bit up. Okay, and let's okay, let's make it, oops. Okay, let's delete that. Okay, I hope this is clearer. I'm not going to enlarge it after all. Okay, so this is P prime. Okay, so we have to apply Newton's second law, but now the direction to the left is the positive one because the object moves to the left. Okay, so P prime over V plus mg sine of theta minus the resistive forces is equal to ma. Okay, so the velocity is given P prime over 12. 12 is the velocity plus 1200 times 9.81 times 1 over 14 minus 260 is equal to 1200 times 1.8. So the problem is now somewhat simpler. So P prime over 12 is equal to, I'm moving everything to the right hand side, 1579.14. So P prime is now 18,949.7 watts, okay, which is less than 20,000 watts. Can you guess why? I'm not gonna tell you why. You can let me know in the comments, okay? I want to see. This is like a critical thinking question. So why is it less? It's the same engine, same van, same weight. So what changed? Let me know in the comments. Okay. Okay. Problem number 2 is a lamina. Okay. So it's mostly just calculations, I would say. So let's go see. The uniform lamina ABCDE shown shaded in figure 1 is formed by joining a rectangle to a right angle triangle. The right angle triangle ABE has AB equals to 2A and BE equals to 12A. The rectangle BCDE has BE equals to CD. Yes, okay, equal to 12A. And BC is equal to ED, and that's equal to D, okay? The distance of the center of mass of the lamina from AC is X bar, okay? Show that X bar is 2A, parenthesis, 2A plus 3D, closing, we close the parenthesis, over A plus D. The lamina has a weight W. Okay, so that's part A, and then we will see how to deal with part B later. Okay, let's start with the mass of AB, the triangle. So I'm gonna do it in this page. It will be useful to do it in the back, in the page where the picture of the lamina is, but there is not enough space. So mass of ABE is 1/2 times the base, which is 2A, plus times the height, which is 12A. Okay, so it's 12A squared is the mass of ABE, and then the mass, the rectangle is BCDE. Okay, so mass of BCDE is simply 12A times D. Okay, so 12AD, is that right? Yes. Okay. Now the triangle, by the way, let me know in the comments if you can take these things for granted, because I am assuming they give you formulas for the centroids of these objects. Okay, so the triangle centroid is 1/3 times the mass, times the height, which is 12A. So 4A from AC. So the centroid should be somewhere here, probably. Okay, for the triangle. Okay, so that's about 4A, say. Okay, and then we need to find the centroid of the rectangle, which is of course in the center. So I mean, you can even draw it. So I don't know if you can take this for granted, but okay, I mean, the centroid is there, right? So 6A. So let me know in the comments, though. I'm gonna try to search actually for the formulas that you can have with you. I mean, that would be useful. So, but I haven't, so I'm sorry about that. So, so the rectangle centroid is at 12A over 2, so 6A. Okay. Now we have to set up the equation of moments. So let's do that. So moments equation tell us that we need to have, for balance, 12A squared, which is mass of the triangle, okay, times 4A, which is the X triangle, okay, plus 12AD, which is the mass of the rectangle, times 6A, which is the centroid, X centroid. Actually, let's write X rectangle, okay. Okay, so this should equal, so the moments, because of these two separate objects, should be equal to the whole mass, which is 12A squared, the total mass, sorry, plus 12AD, so that's the total, M total, times X of the center of mass, okay? So we can actually delete one of the a's. So this gets deleted, 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 okay, because it's a common factor. Okay, and we are left with the equation 48a squared plus 72ad is equal to 12a plus 12d times x bar. Okay, so we can actually cancel. So 12, we can take 12a as a common factor times 4a plus 6d is equal to 12a plus d x bar. So 12 cancels as well. So x bar is 4a plus 6d over a over a plus d. I forgot by now, do they give us this? Yes, they do. Okay, and we have proven what they were asking. Okay, let me know in the comments whether you actually need to prove this before using. So I took for granted the centroid for the triangle and the rectangle. Okay, I think you can, but I'm not entirely sure, so let me know. Okay, let's move on to part B now. A particle of weight W over 2 is attached to the lamina at D. Okay. The lamina is free to rotate in a vertical plane about a smooth horizontal axis through A. Okay. So I'm going to actually use the scheme. So there is an axis perpendicular to the page over there through which the lamina can rotate. Okay. So it can rotate as you look at the lamina from the top, it can rotate on the plane of the page. Okay, this is what is implied, I guess. So the lamina is free to rotate in a vertical plane about a smooth horizontal axis through A. Okay, the axis is perpendicular to the plane of the lamina. So that dot I drew, it's like in the case of the magnetic field, in case you're familiar with. So the magnetic field can be out of the page or into the page, but in both cases, when we draw an arrowhead, the cross, or the dot, or an arrow tail, which is the cross, this means that we are dealing with an axis that is perpendicular to the page. Okay. So where was I? The lamina is free to rotate. Okay, the axis is perpendicular to the plane of the lamina when a horizontal force of magnitude F is applied to the lamina at C towards D. So horizontal means this is the force. Okay, so maybe we use our finger or something else, but the force is that one. Okay, so when a horizontal force of magnitude F is applied to the lamina at C towards D, the lamina rests in equilibrium with the line CD horizontal. Okay, given that D is 4A, find F in terms of the weight. Okay, we forgot to, by the way, we need also the weight. So weight over 2 is applied at D, but this is not the whole picture. We also have the weight of the lamina somewhere here. So let's assume that this is x bar, the x coordinate of the center of mass. So the weight applies at the center of mass. So we have the force weight there. Okay, so with all the forces set up, we can take moments around A. Okay, W over 2 creates a clockwise moment, and the weight also creates a clockwise moment, whereas F creates an anti-clockwise moment. Okay, so the equation is actually I don't have enough space anyway, so I'm gonna come back here and start problem B here. So W over 2 times 12A plus the weight of the lamina times the x of center of mass, which we just calculated. So we have 2A plus the weight of the lamina times the x of center of mass. And in the x of center of mass, we take 2 out as a common factor. So 2A times 2A plus 3D A plus D, this whole expression is equal to F times 2A plus D. Okay, I hope this makes sense because F is 2A plus D from A, X of center of mass is the distance from the pivot A, and so on. Okay, so now let's do some simplification. So that's a 6. Okay, so we have 6AW plus 2AW times 14A, where we use the fact that D is for A here, okay, over 5A. So this A cancels, is equal to F times 6A. Okay, so we have 6W plus 28 over 5W is equal to 6F, or 58W is equal to 30F, which means that F is 29 over 15W. And that's the answer. Okay? Another straightforward problem, but you have to be careful with setting up the equations needed, okay? Especially for the moments problem in part B. Okay, so this was problem 2. We are ready to move on. Okay, problem 3. A uniform rod AB has mass m and length 10A, and you can see the rod right there. The end A is on smooth horizontal ground, and the end B is against a smooth vertical wall. Okay, to prevent the rod from slipping, one end of a light inextensible string is attached to the rod at the point C, where AC is 2A. The other end of the string is attached to the wall at the point D. The string is parallel to the ground and is in the same vertical plane as the rod. Okay, the rod is in equilibrium in a vertical plane perpendicular to the wall. The rod is inclined at an angle theta to the horizontal, as shown in figure 2, where that angle is between 0 and 90. Okay, the tension in the string is T. And the first question, okay, is to show that the tangent of theta is equal to 5 times the weight, mg, of the rod, over 8 times the tension. Okay, so there is a lot going on in this problem. So let us start by writing down all the forces that act on this rod. So first of all, we have the reaction from the wall that I will call R1. Okay, and it's perpendicular. Okay, I don't like it. Let's draw it again. Okay, so let's call this R1, and it's the reaction from the wall. Okay, and if that angle is theta, that angle is also theta. Okay, due to Thales' principle, right? We have two parallel lines intersected by a line between them, so the inscribed angles are the same. Okay, so that's the first force. The second force is R2, the reaction from the floor, okay, which we drew just right there, so R2. Then we have, of course, M times G in the middle, okay, so that's mg, and it's in the middle of the rod, so I'm trying to say that this distance is 5a because the center of mass of the rod is in the middle. Oh my god, that looks larger than the middle, but okay, you get the idea. Okay, the weight is acting at the center of mass of the rod, which happens to be half the rod. Okay, so 5a. Okay, so that's that. And we also have the tension. Okay, so the tension from the string. Okay, so those are all the forces. And for equilibrium, we need the horizontal components of the forces to cancel, and we also need the perpendicular components of the forces to cancel, and we also need the moments to balance. Okay, and we will take moments about the pivot point A. Okay, therefore we need to find the components of all forces that are perpendicular to the rod, okay? Except R2, okay? So R2 we don't care because it acts on the pivot, so it can be ignored, right? So, okay. So for the mass, we can analyze, sorry, for the weight, we can analyze it into a vertical component, and we don't care about the component that acts along, that points along A, the pivot, okay? So, okay, for the weight, actually this angle is theta, okay? So that's theta. Again, for the weight, that angle is theta, and the reason is because this side is perpendicular to this side, and then this side is perpendicular to this side. Therefore, the inscribed angles are equal. I hope this makes sense. Okay, let me remove the extra lines. Okay, so that's mg sine theta, in other words. Okay, now for the tension, we need this component, okay, which is, by the way, what did I do? This is mg cosine theta. I'm sorry, guys, mistakes happen. So that's cosine theta. Then that component that is perpendicular to the rod is t sine theta. And then this component of R1, let me try again. I don't know why it makes it. Okay, I need a straight line. Okay, so that's R1 sine theta. And it's perpendicular to the rod. Okay, so let's set up the problem. So in the horizontal direction, so horizontal, okay, we need the forces to cancel, or in other words, we need T to be equal to R1, okay, because T points to the right, okay, along the x-axis, let's say, and R points to the left, so T is equal to R1. In the vertical direction, we need R2 to be equal to the weight, m times g. And then we need, let me use black, moments about A. By the way, I took the moments about A just because, I don't know. I mean, you can probably work with moments about B, okay? In which case R1 is going to be ignored, and it should work, okay? I didn't try it, but it should work. Okay, so if we take moments about A, R2 is irrelevant. By the way, this is sine theta. I don't know why I didn't write it. Okay, so let's see. From these forces, we have, okay, R1 sine theta wants to turn the rod counterclockwise, mg cosine theta wants to turn it clockwise, and t sine theta wants to turn it clockwise. So let's set up the problem. We have t sine theta times 2a, okay? So the perpendicular component of the tension times the distance from the pivot, which is 2a, okay? Plus, then we have mg cosine theta times 5a, right? Because that's the distance of that component that is perpendicular to the rod from the pivot A. And that whole thing should be R1 sine theta times 10a. So plus mg cosine theta times 5a. And everything should be equal to R1 sine theta times 10a. Okay, so a cancels, as we can see, because it's a common factor. So we get this nice cancellation. Oh, and this is R1, I'm sorry. And I think I misled you earlier because if you take moments about B, no, it should work. You should try it. Actually, someone should try it and let me know in the comments that you got the same result, okay? So anyway, let's continue. We can substitute R1 with T, okay? Because we have R1 is equal to T, okay? So let's continue. So we have 2 times T times sine theta plus 5 mg cosine theta, right, is equal to 10t sine theta. Trying to be careful. So I'm gonna bring 2t to the right hand side and then make the right hand side the left hand side. So 8t sine theta, I hope this is not confusing, is equal to 5 mg cosine theta. By the way, I just remembered at some point in my life, I worked in a really, really nice liberal arts college in Illinois, in the United States. And my chair was the best boss you can have. He was he's a very smart guy, good mentor, good teacher, good professor, etc. So liberal arts colleges are undergraduate institutions in the US. Okay, so they award bachelor degrees in physics and other disciplines. Okay, so the idea is that it's called liberal arts because you learn a little bit of everything. So you learn physics, but you also do philosophy and stuff like that. Anyway, so he used to say that nobody under the age of 25 can do algebra. So I just flashed through my mind right now because I'm performing algebra for high school students. But you guys are really smart, so you get it, right? Let me know in the comments. So let's continue. Okay, so we need to divide sine theta with cosine theta to uncover the tangent of theta. Okay, so this is equal to 5 mg over 8t. So the tangent of theta is 5 mg over 8t. Okay, as requested. Okay, so that's good. So problem A tackled. Let's move on to part B. Okay, part B, a particle of mass 3m is now attached to a point E on the rod, and the rod remains in equilibrium. Given that the maximum tension in the string before breaking is 2 mg and tangent of theta is 4 over 3, find the maximum distance AE. Okay, so let's use orange for the particle, and let's put it over here just because there is space there, okay? So the weight of the sphere is going to be 3 mg. Just like before, we only need the component that is perpendicular, okay? And that angle is again theta because it's the same case as with the weight. So we have the component 3 mg cosine theta perpendicular to the rod, okay? We don't care about the other component because it's along the pivot A. So here in the horizontal direction, nothing changes, okay, with the insertion of the extra particle. Things change for the vertical direction. So now R2 should be equal to mg plus 3 mg. But we don't need that because we take moments about pivot A, so we don't care about the addition of the extra weight. Okay, so you should care, by the way, if you work with pivot B. Okay, you should care about it, I think, right? Yes, because in that case you care about the moments of R2. Yeah, in case you are working with pivot B, you need to worry about the addition of the particle. But for our cases, the only thing that changes is this equation for the moments. We need to add one extra component. So let me show you what I mean. Oh, and let's name the distance of the particle 3 mg from the pivot as x, okay? So let's go set up the equation. So we have the tension from the string times sine theta. So same as before, pretty much, okay? T sine theta times 2a, okay? Plus mg cosine theta times 5a, okay? Plus 3mg cosine theta times x, okay? And this whole thing should be equal to 10, what was it? 10t, 10a and then t sine theta, right? Did I mess up something? No, 10a times t sine theta. Okay, do we have cancellations like before? We don't this time. We need to keep a. So let's keep going. So we have, let me think. Okay, let's do 8at sine theta, where again I'm taking this component to the right hand side, and then I make the right hand side the left hand side. Okay, and this is equal to mg cosine theta times 5a plus 3x. Okay, I hope this makes sense. If it doesn't, ask me in the comments and I will provide explanations. So 5a plus 3x is equal to 8at over mg times tangent of theta. Okay, and they tell us that right before things break, the maximum tension is 2 mg and tangent of theta is 4 over 3. So we will plug those in. So we have 5a plus 3x is 8a times 2mg over mg times 4 over 3. So we have 5a plus 3x is equal to 64a over 3. Okay, so we have 3x is equal to 49a over 3. So x is 49 over 9a, or x is 5.44a. Okay, so we put the particle on the right of the center of mass. Okay, and we were actually right because it's 0.44a to the right of the center of mass. So the position is actually that we used was actually perfect. Okay, this is a difficult problem to explain on an iPad screen. Okay, so if something's not clear, ask me in the comments and I will explain further if needed. I hope this makes sense. This was a hard problem because there were many components of forces that needed an analysis and so on. Okay, I hope this made sense. So let's move on. Okay, question 4. In this question, I and j are perpendicular horizontal unit vectors and position vectors are given relative to a fixed point O. The velocity of a particle p at time t seconds where t is larger than 0 is given by that expression that you see in your screens. Question A, find the value of t when p is at instantaneous rest. So we have to set either the x component, which is the black one, or the y component equal to 0, find the time, and then plug into the other equation to see that we get 0. Okay, so we have to set either of the two components equal to 0. Okay, so let's start with the x component. So 6t minus 25, this problem A, okay, minus 25 times the square root of t plus 14 is equal to 0. So let's take the square root to the other side. So 6t plus 14 is equal to 25 root t. And now let's take the square of both sides. So we have 36t squared plus 196 plus 168t, where I expanded this square, I guess. Okay, this is equal to 625t. Okay, let's bring everything to the left hand side. So 36t squared minus 457t plus 196 is 0. So t12 is 457 plus or minus root 180,625 over 72, which yields 457 plus or minus 425 over 72. So we get T1 is 0.44 seconds and T2 is equal to 12.25 seconds. Okay, let's plug T1 into the y component and see if we get 0. Okay, so plug T1 into y component, excuse me. So we have 8 times 0.44, okay, minus 30, and then the square root of, okay, the square root of 0.44, and then what is that, plus 7, excuse me, I hope I didn't make you dizzy. Okay, let's see, this should be equal to 0. Okay, so this gives us minus 9.38. Okay, so that's wrong. Okay, so T1 is not the solution. Let's try T2. Okay, so we have 8 times, what was it, 12.25? So 8 times 12.25 minus 30 times root of 20 point, sorry, did I say 20? I mean 12.25, excuse me, okay, plus 7. Okay, let's calculate this. This yields exactly 0, okay? So T equals to 12.25 seconds is the time at which we have instantaneous rest. This, yeah, I mean, it's going to come to instantaneous rest and then keep moving, okay, because we have a T dependency. Okay, so let's go back and work with problem B. Okay, part B, find the value of T when the acceleration of P is perpendicular to 2I minus J. Okay, so this is the velocity vector. Let me delete this. So we are given the velocity vector, okay? So the acceleration is the first derivative of the velocity vector. So let's start by doing that. So let's calculate the acceleration vector, which is the first derivative of the velocity vector, okay? And this will be equal to the constants drop out, and we have 6 minus 25 over 2 root t I hat, okay, plus I hat is the unit vector, okay, plus 8 minus 30 over 2 root t times j hat, okay. Now we are told that what are we told again? So find the value of t when the acceleration of p is perpendicular to 2I minus j. Perpendicular means perpendicular means that the acceleration vector dotted with 2I hat minus j hat is 0. Okay, let's do that. So we have, let's take square brackets, 6 minus 25 over 2 root t I hat plus 8 minus 30 over 2 root t. Actually, it should be 15. I don't know why I keep doing that. So j hat, okay, dotted with 2I hat minus j hat is 0. So we take the dot product of this component with this, and then of this component with this component. Okay, I hope this makes sense. And we end up with the following: 12 minus 25 over root 2 minus 8, okay, plus 30 over 2 root t is equal to 0. So we have 4 is equal to 10 over root t. So root t is 10 over 4 So we take the square, so t is 100 over 16 or 6.25 seconds. That's the answer. Okay. Okay, now part C starts right there. So when t is 1 second, p is at the point with position vector 1/3 I hat minus 7 j hat meters. Find the distance OP when t is 4. Okay, so that's part C. Okay, it will involve several calculations. So anyway, if we run out of space, I'm going to use an extra page. So let's start. So let's write the velocity vector can be written as dr over dt, where r is the position vector. And this thing is equal to, I mean, it's what they give us. So 6t minus 25 root t plus 14 I hat, okay? And then plus the j component, which is 8t minus 30 root t plus 7, and that's j hat. Okay, so dx over dt, we will first integrate to find x and y, okay, because this is dr over dt. Actually, okay, I made it a little bit cryptic. So we can write this dr over dt as dx over dt I hat plus dy dt j hat, and then this is equal to that, so the purple, and then the orange is equal to that, okay? And we can, oops, the I hat is not included, okay? So we will need to solve these differential equations by simple integration to find x and y first, and then see how to deal with things. So dx over dt is 6t minus 25 root t plus 14. So we can integrate dx is equal to this integral, 6t minus 25 root t plus 14 dt. So x is 3t squared plus 14t minus 50 t to the 3 halves over 3, oops, minus 50 t to the 3 halves over 3 plus cx, okay? Similarly, I'm not going to show it because I want to save time. Y is equal to 4t squared plus 7t minus 60t to the 3 halves over 3 plus cy, okay? Now, we need to find cx and cy. How can we do that? Let me use an extra space. So we can do that using this information. When t is 1, p is at the point with position vector, that one, okay? So let's use that. So at t equals to 1 seconds, the position vector r is 1/3 I hat minus 7 j hat. Okay, so we have for the x component 3 plus 14. So I'm taking this x component and I plug in 1. So I have 3 plus 14 minus 50 over 3, right? So minus 50 over 3 plus cx, and this whole thing should be equal to 1/3, okay, this component, okay? So this means that cx is actually 0, okay? Similarly, for the y component, we have 4 plus 7, so this is the x component and this is the y component. So 4 plus 7 minus 20 plus cy is equal to minus 7, which works out so that cy is 2, okay? So r is 3t squared plus 14t minus 50t to the 2/3 over 3 I hat plus 4t squared minus 7t minus 20t to the 3 halves. By the way, this is 3 halves earlier. I'm sorry, guys. That's 3 halves. Okay. Plus 2 j hat. Okay. So r at t equals to 4 seconds, we just plug the time in, ends up being minus 88 over 3 I hat minus 66 j hat. Okay. And then OP is the square root of minus 88 over 3 squared plus minus 66 squared. So this is equal to 72.22 meters. Okay, a little bit of an involved problem, but if you're careful with integrations, you will do fine. Okay. Okay, question 5. At time t equal to 0, a stone S is excuse me, is projected from a point A on the top of a cliff. The point A is 120 meters above horizontal ground. The stone S is projected with speed 25 meters per second at an angle of 60 degrees above the horizontal. The stone S is modeled as a particle moving freely under gravity. Okay. For the motion of S from A until it first hits the ground, find the maximum height above the ground reached by S. Okay, in this problem, it's useful to draw a scheme, even though it's not a very complicated situation, but it always helps to visualize what's going on. Okay, so this is the hill. Okay, so are the 120 meters stated. Okay, and this is our, what is it? This is the rock or a stone. Okay, that's the stone. Stone S. Okay, and the other information we are told is that we have an initial velocity of 25 meters per second, excuse me, and 60 degrees is the launching angle. Okay, first of all, let's do some simple calculations here. So let's find the x component and the y component of the velocity. So let's call them ux and uy, and I call it u because in Edexcel u is the initial velocity. So ux is 25 cosine of 60 degrees. So 12.5 meters per second is the horizontal velocity. The vertical velocity is uy is 25 sine of 60 degrees, or 25 root 3 over 2, or 21.65 meters per second. Okay. So we can use Suvat equations here, by the way. So that's root 3. I'm sorry. Okay. So for part A, let me turn the page. So for the vertical velocity, you have that Vy is ux. Sorry, what am I saying? The velocity, the vertical velocity, the velocity in the y direction is equal to the initial velocity in the y direction minus, actually plus at, which you can write as uy minus gt, and it's a minus because the vertical component of the velocity moves up while g points down. Okay, so the velocity decreases as we move up. Okay, so we will use this to find the time to reach the maximum height, and then we will find that maximum height. So at maximum height, okay, Vy is going to become 0. Okay, it's going to come to an instantaneous stop. Okay, up in the air at the top position, at the maximum height. Okay, which means that t is going to be uy over g, in other words, or 21.65 over 9.81. So 2.21 seconds is the time needed to reach the maximum height. What will that maximum height be? It's going to be y equals to uy times t, and then plus 1/2 at squared, where we have to use minus again because we are moving up while g points down. Okay, so we will have uy times t minus 1/2 gt squared, and now we plug in uy is 21.65, time is what we just calculated, 2.21, minus 1/2 9.81 times 2.21 squared, and this works out to be 23.89 meters. You are not done yet because y is measured from the stone, the position of the stone, which is 120 meters above the hill. Okay, so max height is 120 plus 23.89, or 143.89 meters above the ground. And this was problem A. Okay, done. Okay, part B, find the direction of motion of S when t is 5 seconds. Okay, before we do that, we need to think a little bit. So remember, the stone takes 4.42 seconds to go all the way up and then down. Okay, so when it reaches this point, okay, it's like having the same, it will have the same velocity. So u is going to be 25 meters per second. I hope I make sense, but you can use symmetry arguments. So, okay, so the rock will have u equals to 25 meters per second once it travels for 4.42 seconds, which is this time over here. Where was it? Here. Okay, it's the time for the rock to go all the way up and then all the way down. And then once it makes it all the way down, it's going to have the same velocity as before due to conservation of energy, right? But pointing down. And now 60 degrees is going to be this angle. Okay. Oops. What am I doing today? I know, I'm sorry, guys. I'm a little bit under the weather. I don't know if that affects things. So that's 60 degrees. And the velocity is again 25 meters per second, but now it points down. Okay, so we have, in other words, we have a horizontal component, which is the same right before, right? So we will have a ux, which is 12.5 meters per second, and we will have a uy, which is now 21.65, but it points down, okay? So it's important to recognize the fact that the situation kind of reverses, okay? And we have to find out what is going to happen to the velocity in the y direction once, because in the x direction it doesn't change, in the y direction for the rest 5 minus 4.42 seconds, okay? So let's write a few things down. So B, okay, at 4.42 seconds, okay, S will have uy equals to 21.65 seconds traveling down, okay? So we can use Vy equals uy plus gt, because now it accelerates down, okay? So the velocity is gonna be increasing, okay? For time equal to 5 minus 4.42 seconds, okay? Which is 0.50, okay? So Vy is 21.65 plus 9.81 times 0.58, which yields 27.34 meters per second. And the situation is now the following. We have Vx, which is constant, equal to 12.5 meters per second, and then Vy points down now, okay? So Vy is Actually, it should be minus 27.34 meters per second. And to find the direction, we need to calculate this angle theta. So tangent of theta is minus 27.34 over 12.5, which means that theta is minus 65 degrees. Okay, and that's the answer. That's the direction. Okay, so it's going to be minus 65 below the horizontal, or you can say it's 25 degrees from the vertical or something like that. Okay, so this requires a little bit of thinking. I mean, part B. Now let's move on to part C. Okay, so in C they ask, find the length of time for which S is moving at a speed greater than 25 meter per second. Okay, so basically, okay, it's a little bit weird again, so I have to explain. So it starts with 25 meters per second. Okay, I'm gonna use the green color to see what I'm doing. So it starts with 25 meters per second, which is, I mean, 25 meters per second is not greater than 25 meters per second. Okay, I hope this makes sense. So the velocity decreases as it moves up, and then it increases back to 25 meters per second once it makes it at the height of 120 meters, meaning that the moment it crosses down and it starts covering that 120 meters distance. So from that moment on, so after 4.42 seconds, it will have a velocity greater than 25 meters per second. So you have to find the time needed for the object to start from 120 meters, travel down to the ground, pretty much. Okay, I hope this makes sense. So how are we going to do this? Is there space? There is space. Great. Okay, so part C, we basically have to use that the fact the Savat equation S is U times T plus 1/2 GT, AT squared, okay, plus 1/2 AT squared. But this time we will use, so we will set S as the height in the Y direction. So the height is going to be equal to Uy times T plus 1/2 GT squared. And we use the plus because we move down, okay, in the same direction as the acceleration. Okay, so the height we need to cover is 120 meters, okay. So this should be equal to Uy, which is 21.65 times T plus 1/2 times 9.81 T squared. Okay, so we have T squared. So I'm gonna go a little bit fast now. So actually, no, I'm not gonna go fast. So actually, let me help you a little bit. So 120 is equal to 21.65 T plus 4.91 T squared. And then we will divide everything with 4.91. So T squared plus 4.41 T minus 24.46 is equal to 0. So T12 is minus 4.41 plus or minus the square root of 117.29 over 2, okay, which eventually yields T12 is equal to minus 4.41 plus or minus 10.83 over 2, which means we keep only the positive root. So T is 3.21 seconds, okay? Okay, so, but the most important thing here is, again, to understand that it takes 4.42 seconds to go up and down, and then the time needed is the time to go and hit the ground, pretty much. approach. Okay, so it needs a little bit of a physical intuition here. Okay, this was problem 5. We are ready to move on to problem number 6. Okay, question 6. Two particles P and Q lie at rest on a smooth horizontal surface. The mass of P is 5m and the mass of Q is 3m. Particle P is projected towards Q with speed 3u and the particles collide. The coefficient of restitution between P and Q is E, where E is larger than 0. Part A, show that the speed of Q immediately after the collision is 15u over 8 times 1 plus E. Okay, so let's set up the problem. So part A, so we have before, okay, so we have the surface, I guess, and we have the particle P of mass 5m and the particle Q of mass 3m, right? Yes, okay. And the particle P travels to the right with velocity 3u. I don't know why I made my 3 so weird. Let me redo it. Okay, 3u. Okay, after we have the following situation. Okay, this is the floor again. So we will have the mass P of the particle P with mass 5m traveling with some velocity Vp to the right, and Q will be traveling with some velocity Vq to the right as well, okay? And initially the speed is 0 for Q. Okay, I hope this makes sense. So, first equation, momentum conservation. Momentum conservation. This is a linear momentum. I don't know if you guys cover 2D collisions, let me know in the comments, but this is linear, so one dimension. So we have 15, so we have pretty much 5m times 3u is equal to 5m times vp plus 3m times vq. So that's our equation 1. Now, the restitution equation. So restitution. Okay, I had to look this up because I never really dealt with something like this, but it makes sense, of course. Okay, so E is equal to the ratio of the speed of separation, okay, over the speed of approach. Speed of approach. Okay, so E is the speed of separation is simply VQ minus VP, okay, after the collision, okay, because the object Q has to be traveling a little bit faster than the P, right? And the speed of approach is simply the speed with which P collides with Q, which is 3. Oops, I don't know what's wrong with my 3's today. So 3U. Okay, so this equation 2. Okay, so actually, let's expand a little bit. So we have 3UE. 3UE is equal to VQ minus VP. So VP is VQ minus 3UE. And now again, this equation 2. And from 1 and 2, we get that 15m times u is 5m. Let me think, what did I do there? Okay, yes, we have 5m times vq minus 3ue plus 3m vq. Okay, I hope this makes sense. So we can do 15 mu is equal to 5 mvq minus 15 mue plus 3 mvq, okay, which yields 15. First of all, okay, let me see, 3. Okay, that's M, by the way. Okay, so M. So M cancels. Okay, I forgot about that. So 15U times 1 plus E, I bring this term to the left-hand side, is equal to 5 plus 3 is 8VQ. Okay, so this means that VQ is, let me see, 15U1 plus E over 8, okay, which is what they ask. Okay, great. Part B, show that after the collision, P and Q move in the same direction. Okay, so we calculated VQ, so let's see, let's pretty much find VP. Okay, so part B, okay, we have VP, we're going to use equation 1, okay, so we will use this equation. So no, we will use equation 2. What am I saying? I'm sorry, guys. Sorry. So VP, oops, VP is VQ minus 3UE, which means that VP is equal to 15U1 plus E over 8 minus 3UE, okay, which is equal to 15U over 8, okay, and then plus 15UE over 8 minus 3UE, which yields 15U over 8 minus 9UE over 8. And this thing is equal to 3U over 8 times 5 minus 3E. Okay? But 5 minus 3E is larger than 0 since E is less than or equal to 1 and larger than 0. So at most, if E is 1, then 5 minus 3 is 2, which is larger than 0. So VQ is larger than 0 and VP is also larger than 0. So they travel to the right. Okay, so I hope this makes sense. VQ is positive because 1 plus E can at most be equal to 2. Okay, so that's a positive velocity. And then VQ is also positive. Sorry, VP is also positive. So both are positive. So they move to the right. So that's it. Okay. There is also part C, which starts over here. So after the collision, Q collides with a smooth, fixed vertical wall, which is perpendicular to the direction of motion of Q. The coefficient of restitution between Q and the wall is 1/2. In the collision with the wall, Q receives an impulse of magnitude 45 mu over 4. Find the value of E. Okay, so this is actually a difficult problem, I have to say, but we will tackle it. So this part C. So we start with VQ equal to 15U over 8 times 1 plus E. Okay, so after bouncing, okay, VQ prime is minus E wall, okay, which is the coefficient of restitution of the wall, times VQ. So we get, what was it, 1/2, right? Yes, so this is what I will use right now, okay? So VQ prime after the collision with the wall is minus 1/2 times 15U over 8, 1 plus E, or minus 15U over 16 times 1 plus E, okay? Now, impulse is equal to change in momentum to delta P, okay? So we have So we have impulse is equal to change in momentum. Now let's find delta P. I'm sorry if I confused you. So delta P is 3m times VQ prime minus VQ, okay, which is, this is the final momentum, 3m VQ prime, minus the initial momentum, which was minus 3m VQ, okay? So this is equal to 3m times minus 15u over 16 times 1 plus e, minus 15u over 8 times 1 plus e, okay, which ends up being equal to 3m times 1 plus e times, what am I doing? Times 15, or let's keep it because now I'm confused. Minus 15u over 16 minus 15u over 8. Okay, so that's delta P. So delta P is minus 3m1 plus e times 45u over 16. There you go. Okay, and now they tell us, okay, I will need a clean page. Now, impulse is delta P, okay? So this means delta P is given as 3m, oops, no. Delta P is, yes, let's do this, okay? So impulse is equal to the absolute magnitude of delta P, okay? So 45m u over 4, which is the impulse, is equal to 3m times 1 plus e times 45u over 16. So we get nice cancellations. So u cancels, m cancels. We find 45 over 4 is 135 over 16 times 1 plus e. So 1 plus e is 4 over 3, which means that e is 1 over 3. Okay, and this was problem 6. So I think another hard problem. Okay, so we are ready to move on to the next problem, which is the final one in this paper. Okay, so let's move on to problem number 7. Okay, problem 7, we have pulleys and inclines, and yeah, it looks like a nightmare. So figure 3 shows a rough plane inclined at an angle, is that A or alpha? Okay, let's call it alpha, to the horizontal, where tangent of alpha is 5 over 12. The plane is fixed to horizontal ground. Okay, a small smooth pulley is fixed at the top of the plane. One end of a light inextensible string is attached to a particle A that is held at rest on the plane. The string passes over the pulley, and the other end of the string is attached to a particle B that hangs vertically below the pulley. The string from A to the pulley lies along a line of greatest slope of the plane. Particle A has mass 2m and particle B has mass 5m. The distance from B to the ground is d. When the system is released from rest with the string taut, A begins to move up the plane, and in the subsequent motion, A never reaches the pulley. Okay, the coefficient of friction between A and the plane is mu. The work done against friction as A moves a distance d up the plane is 3 times m times g times the distance over 13. Question A, find the value of mu. Okay, so let's start by analyzing the forces here. So I'm going to use red color for whatever reason. So we have the weight of the particle A, 2mg, the reaction from the floor, N, okay, We have the tension from the string pulling it up, T, and we also have the friction. Okay, so oops, so that's our free body diagram. So we have the friction is in the opposite direction from the tension. So that's our friction. And since we are interested in the motion along the incline, we need to analyze, we need to analyze into these two axes. Okay, maybe I will draw this, okay, and this. Okay, so in the perpendicular axis, which is somewhat of our, let's call it y prime and x prime, if you will. Okay, so if that angle is A, then this angle over there is also A. I mean, we did this earlier. And this component is 2mg cosine alpha. Okay. And therefore, this component of the weight, which is along the friction, is 2mg sine of alpha. Okay. And then for object B, I don't know if we will need it, but we also have the tension that pulls up. It's the same tension as the tension that pulls particle A up, okay, because they are connected through the pulley. And we also have the weight of this guy, which is 5 mg. Okay. Okay, so what do we have? So let's start problem A. So the work against friction is 3 mg times d over 13. But this work is actually F times the friction, right? I mean, the work done against friction is actually the friction times distance, okay? So F times D is 3 times mg over 13 times D. So this cancels actually. And now friction is equal to the coefficient of friction times the reaction from the floor, which I called N, okay? And this is equal to 3 mg over 13, okay? But N, notice that N is equal to, N is 2 mg cosine of alpha, right? So we have, because there is no motion in the y prime direction, okay, it's not jumping up and down, okay. So so N is balanced by the component of the weight along the y prime axis. So mu times 2 mg times cosine of alpha is 3 mg over 13. So let's cancel a few things. So this cancels and g cancels, okay. So we find that 2 mu is 3 over 13 cosine of alpha. Okay, and here allow me to be a little bit of a nerd. Okay, so we are given that tangent of alpha is 5 over 12. Okay, which means that sine of alpha is 5 over 12 times the cosine of alpha, right? Which means that sine squared of alpha is 25 over 144 times cosine squared of alpha. You will see where this goes. Okay, so we can write though sine squared of alpha as 1 minus cosine squared of alpha. And this is equal to 25 over 144 cosine squared of alpha. So you will see, so we get 169 over 144 cosine squared alpha is 1, which means that cosine of alpha is plus or minus 12 over 13, and we keep the positive, so cosine of alpha is 12 over 13, which means that sine of alpha is 12 over 13, which is cosine of alpha, times tangent of alpha, which is 5 over 12. So 5 over 13. And if we plug back to mu, we get 2 mu is equal to 3 over 13 times 13 over 12. So 3 over 12 is 1 over 4. So mu is 1 over 8. And it's elegant. Okay, B. What was B? So, okay. So B starts over here. The speed of B as it hits the ground is V, capital V. Okay. Use the work energy principle to find an expression for V squared in terms of G and D. Okay. So, so let's think about this. So this is part B. Okay, we have that the work done is equal to the change, to the total change in energy. Okay, so for particle B, we have work by gravity. So we have gravity equal to 5 mg times d. Okay, and from the tension, we get minus tension times d. And the reason why it's minus, it's because the tension pulls it up. Okay, so gravity goes down, so 5 mg times d is the work done by gravity, and tension goes up, so minus t times d is the work done by the tension. So for particle A, let's find the work done. So the associated energies I'm trying to say. So particle A, okay, we have, okay, if we see the forces here, 2 mg pulls to the left, okay, and friction pulls to the left, and then tension points to the right. Okay, so let's find all the work done. So that's a plus there. Okay, so for particle A, we have minus 2 mg sine A times d from gravity. So this is the work done by gravity. Okay, bear with me, it will work in the end. We have t times d, okay, from the tension, okay, and it's plus because it points to the right in the same direction as the motion. Okay, so the motion is to the right. Okay, remember that. So tension, so the motion is to the right, so we have to take the dot product, right? So t times d is the work done by the tension in the case of particle A, but for particle B, it's minus because the motion is down and the force is up. Okay. And what else? And the friction. I forgot the friction. So minus 3 mg d over 13 is the work done by friction. Okay, how do we know that? They give us that, remember? So the work done against friction is 3 mg d over 13. So the work done by friction is minus that. Okay. Okay, so we have everything. So let's calculate T total. Okay, let's turn the page. Sorry, got distracted. So the total work, okay, is 5 mgd minus t times d minus 2 mg sine A times d plus t times d minus 3 mg d over 13. Okay, and we get this nice cancellation of the tension term, which is nice. And in the end, I'm gonna skip a step and give you the final result. That's 4 mg d. Okay. Now, the total energy, so delta E kinetic, okay, is equal to the final kinetic energy minus the initial kinetic energy. Okay, the final kinetic energy is 1/2 times 2m times v squared, which is the velocity of particle A, plus 1/2 m times v squared, okay? And then minus 0 because it starts from rest, okay? And this change in kinetic energy will be equal to the work that we calculated, okay? So it's a little bit of a crazy calculation. So delta E kinetic is equal to the work. So we get 7 mv squared over 2 is equal to 4 mgd. So m cancels, and we find v squared is 8gd over 7. We still have part C. So part C is here. Find the speed of A when it has moved a total distance of 2d up the plane, giving you an answer in terms of g and d. Okay. So let's think about that. So C. So the moment B touches the ground, okay, v squared is 8gd over 7 4a, okay, and it already covered a distance d. Okay, I hope this makes sense. V squared is the common velocity for the two objects, okay, until this guy B hits the ground, okay. At the moment B hits the ground, A has a velocity of 8gd over 7, okay, and that's it, and that's the initial velocity, okay, of A. So let's write that down. So u for A is u square is 8gd over 7, okay. It will cover another d, okay. With acceleration, we need to find its acceleration, okay, the acceleration of A. So to calculate the acceleration, we need to work out the forces on A. So tension is gone, okay. So we will have pretty much, where was it? Okay, we will have 2mg times sine A plus the friction is equal to the new acceleration. I hope this makes sense. Let's write that down. So for the acceleration, we will have 2mg sine A, okay, plus mu times 2mg cosine A, and I remind you that this is the reaction force, okay. This is going to be the new acceleration, so 2ma, okay. So the two cancels, so 2 cancels and the mass cancels. So A is g times 5 over 13 plus 1/8 g times 12 over 13. So g over 2 is the new acceleration, and it's down, right? It's deceleration, actually. So we will have v squared for A is going to be equal to ua squared, which is this quantity up here, plus 2as. So we get, let's use another clean page, v squared is 8gd over 7 minus g over 2, because it's deceleration, times 2 times d, the distance that it covers. So v squared is going to be GD over 7. So it will reduce, which makes sense as we have this equation now, okay? And to understand this, you have to come back to the forces over here. And in part C, this tension is gone because particle B touches the ground, so the string is not taut anymore, so tension is gone from there. But we still have the component of the weight of 2m pushing it down and the friction also pushing it down. So we will have a deceleration equal to, as we proved, g over 2, okay, over here. And then we use Suvat to find the final velocity, which is gd over 7, which is less than the initial velocity, which was 8 gd over 7, okay, which was the initial velocity of particle A. Okay, I think this was a difficult paper. Forgive me if I made some mistakes or if my explanations are not as perfect as you expected them to be, because this is the first Mechanics M2 paper for me. So I'm still trying to figure out, figure my way around these papers. This was fun to solve. It's a challenging paper. Okay, and okay, enjoy your summer. I'm gonna try to keep uploading videos, but there will be some priority on new topics that might not be related to high school physics. It will still be physics probably. So yeah, I'm trying to keep evolving my channel, if that makes sense. I want to thank that one viewer that bought me a coffee through the Buy Me a Coffee link. I have the Buy Me a Coffee link in all of my video descriptions and also in the channel description. So any contributions to this effort will be welcomed because I have to survive somehow to keep doing this. Thank you guys for all your nice comments. The priority is physics, okay, for this channel, but occasionally I will delve into mathematics, I'm sorry, because I really love math, and we will see how this goes. So